There's a question that seems simple, but the more you think about it, the more it resists an easy answer. The question is this: why do some people learn certain things easily and others don't? And the answer most people give themselves, almost automatically, is intelligence. Some have more, others have less. Case closed. But Richard Feynman didn't accept answers that ended before they even began. He had a deep distrust of explanations that seem to explain, but, when you press a little, reveal that they explain nothing. And intelligence, as most people use the word, is exactly that kind of explanation. You ask why someone can't understand physics, and the answer is because they're not intelligent enough. But that's like saying a medicine works because it has healing properties. The word sounds like an answer, but it says nothing substantial. Feynman spent a good part of his life thinking about learning, not in an abstract way, not as an educational philosophy, but in the way he thought about anything, with thought experiments, with concrete examples, with active distrust of conventions. And what he found when he looked closely at how people learn science, especially physics, was something that genuinely disturbed him. Most people weren't failing to learn. They were being taught to imitate learning without actually learning. This isn't a motivational critique. It's not the kind of thing someone says to energize an audience. It's a technical observation. And to understand what it truly means, you need to understand a little about how knowledge works. Not how we want it to work, but how it actually works. Let's start with something concrete. Imagine you're learning what energy is. Someone tells you, energy is the capacity to do work. You memorize this definition, you write it on the test, you get the question right. But here's the problem. Do you know what this sentence means? Not the sentence itself, which you memorized perfectly. Do you know what work means in this context? Do you know why energy and work are related? Could you explain this to an 8-year-old using only objects from your kitchen? If the answer is no, then you've learned the words, but not the concept. And there's a huge difference between these two states. One allows you to solve new problems, the other only allows you to repeat what has been taught. Feynman, at different points in his life, called this knowledge without content. He had a favorite example he used when teaching at Caltech, which appears in different forms in several of his lectures. He talked about how children in Brazil, where he taught for a time, could recite definitions of optics with absolute precision, but when you took a real lens and asked what it would do with light, they didn't know. The knowledge was packaged in the right words, the correct technical terms, the right way to write the equation, but the connection between that set of symbols and the real physical world simply didn't exist. And here's the part that troubled Feynman. This wasn't the children's fault. It was the predictable result of a teaching method that rewards reproduction instead of understanding. If an educational system tests you on your ability to repeat definitions and you're intelligent, what are you going to do? You're going to optimize for repeating definitions. You're going to learn to recognize the patterns in the questions and produce the answers those patterns expect. That's rational. That's exactly what an intelligent person would do within those rules. The problem is that this process produces something that looks like learning on the outside, but is empty on the inside. And when you, later in life, try to use this knowledge to solve a problem that wasn't pre-formatted in the same way as the exam problems, the knowledge isn't there. Not because you forgot it, but because it never existed in the form that would be necessary for it to be applied. Now consider what happens to the person who has gone through this process for 12, 15, 20 years of formal education. What does she learn about herself? She learns that when questions are in the right format, she can answer them, and when they aren't, she can't. And the natural conclusion, the conclusion that makes sense given what she has observed about herself over the years, is, I must have a limit. I must not be as intelligent as those other people who seem to understand everything. But what she's confusing is a methodological flaw with a failure of ability. She's looking at the results of a specific, poorly calibrated teaching process and drawing conclusions about her own nature. That's a logical fallacy, an understandable error, almost inevitable given the context, but an error nonetheless. Feynman was obsessed with the difference between knowing the name of a thing and knowing the thing itself. He tells a story about his father, who was a uniform salesman, but who taught young Richard to look at the world in a particular way. When they saw a bird, His father didn't just say its name, he would say, "I can tell you the name of this bird in 10 different languages, and at the end of it, you won't know absolutely anything about the bird. You'll know what humans in different places call this animal. But the bird itself, what it does, why it does it, how it finds food, how it flies, that's something completely different." This is the core of the Feynman method, although he never called it that. It's the idea that understanding is different from naming, and that most of what we call education is, in practice, sophisticated training in naming things accurately. And this is where physics comes in, not as a school subject but as a way of thinking. Physics, in its essence, is the attempt to understand how the world works based on principles, not memorized rules, but principles that you have truly internalized to the point that you can derive rules from them when needed. Feynman said that if all of science were destroyed, and you could only save one sentence to pass on to future generations, that sentence would be, "Everything is made of atoms, tiny particles that are in constant motion, attracting each other when they are slightly apart and repelling each other when compressed." He said that with just this idea, carefully thought out, you could reconstruct an enormous amount of scientific knowledge. This is the kind of understanding he valued. Not the knowledge you need to consult, the knowledge you can use, the knowledge that is connected to the world in a way that allows you to draw new conclusions from principles you truly understand. Now consider what happens when a person who has been trained to name things tries to learn physics. They are given an equation, for example, Newton's second law. Force equals mass times acceleration. They memorize it. They learn when to apply it. They learn the types of problems in which this equation appears. But they never ask, what is this equation saying about how the world works? Why do mass and acceleration have this specific relationship? What would happen to the universe if this relationship were different? These questions don't appear on the exam, so they aren't asked. And the consequence is that the equation remains a symbol, not a thought. It occupies a space in memory, but not a space in understanding. Feynman had a technique for testing whether someone truly understood something. It was simple and unforgiving. He would ask the person to explain the concept as if they were explaining it to someone who had never heard of the subject, without using the specific technical jargon of the field. If the person could do this, they probably understood. If they couldn't, chances were they were repeating a learned structure without having access to what lay beneath that structure. What this reveals is not a lack of intelligence. It reveals the absence of a specific step in the learning process, the step in which you translate the concept from the format in which it was presented to a format that makes sense to you. This step, which is the most important of all, is exactly what conventional teaching most often skips. And here's the central point that needs to be stated clearly. This step isn't skipped because the teachers are bad or because the system is malicious. It's skipped because it's difficult to test, difficult to standardize, difficult to consistently assess in a class of 30 students. It's much easier to ask what the formula for kinetic energy is than to ask a student to explain, using only words, why a faster object has more energy than a slower object. The second question reveals much more about real understanding, but it's much more laborious to correct. So the system follows the most efficient path for the system, not the most efficient path for learning. And the people who go through this system carry, upon leaving it, a mistaken conclusion about themselves. There's another aspect to this that's important, and that Feynman touched on several times: the issue of error. In the process of real understanding, making mistakes is essential, not in the sentimental way people sometimes talk about mistakes, as if making mistakes were intrinsically valuable. Making mistakes is valuable because when you make a mistake and you know you made a mistake, you have information about where your understanding is failing. The error is a signal. It's telling you something specific about the state of your mental model. But in a system that punishes error with low grades, failing grades, and social judgment, the student learns not to risk understanding. He learns to reproduce what he is sure works. He learns not to try to derive ideas, not to try to understand in other ways, not to try to connect with things he already knows, because any deviation from the known path is a risk. The result is a person who knows a lot and understands little, who has a great capacity for pattern recognition within trained contexts, and a low capacity for reasoning outside of those contexts, and who, when faced with a genuinely new problem, becomes paralyzed not due to a lack of intelligence, but due to a lack of practice with the actual process of thinking. Now, what does physics have to say about this from a more fundamental point of view? There is a connection here that is not metaphorical. It's a real connection to how information works. The human brain is, among other things, an information processing machine, and like any system that processes information, it operates according to certain principles. One of them, which has been increasingly studied in neuroscience and information theory, is that the brain does not store facts independently. It stores relationships. Memory works through connections. The more a piece of information is connected to other information, the more it is integrated into a network of relationships, the more accessible it is, and the more useful it becomes. This has a direct implication for learning. A fact memorized in isolation, without connection to anything else, is much more fragile than a concept that is understood, which is connected to other concepts, which has implications that you have explored, that you have verified against real examples, that you have tried to explain in other ways. Understanding is not just a qualitatively different state from memorized knowledge. It is quantitatively more robust, more accessible, and more generalizable. Feynman understood this intuitively, without necessarily using the vocabulary of neuroscience. When he said he wanted to truly understand something, he was describing exactly this process of building connections. He didn't stop when he could use an equation correctly. He stopped when he could see the equation as an inevitable consequence of something more fundamental that he had understood beforehand. And there's something about this approach that has a very specific quality, which is the capacity for surprise. When you truly understand something, the implications of that understanding often surprise you. You discover connections you didn't expect. You see that two seemingly unrelated phenomena have the same underlying structure. You realize that something that seemed obvious isn't as obvious as it seemed, and that something else that seemed impossible to understand actually makes perfect sense when you see it from a different angle. This pleasure of intellectual surprise was what Feynman called beauty. Not an aesthetic beauty, although he was capable of articulating that kind of beauty as well, but a structural beauty. The feeling that the world, when truly understood, has a coherence and an elegance that the embellished version of it never reveals. The question that remains, then, is not whether a specific person is intelligent enough to understand physics. The more interesting and more honest question is, has this person ever had the opportunity to experience the actual process of understanding? Have they ever had the experience of building an understanding from the bottom up, starting with questions that make sense to them, going through the productive discomfort of not knowing, arriving at the moment when the pieces fit together not because someone said they fit, but because they can see why they need to fit together? Most people have never had this experience within a formal educational setting, and without having had this experience, it's extremely difficult to know that it's possible. Feynman said, with a conviction that clearly came from direct experience, that virtually anyone can understand physics. Not the cutting-edge physics, not the most advanced mathematical formalism, but the core concepts, the fundamental ideas of how the universe works. He wasn't saying this as a vague compliment to human ability. He was saying it as a technical statement about what physics is and about what understanding it requires. What understanding requires is time, patience with uncertainty, a willingness to ask seemingly naive questions, and an environment that treats error as information rather than failure. None of these things depend on innate ability. They all depend on conditions that can be created. The question that remains open, and that each person needs to answer for themselves in some way, is what to do with this information. Because there is a difference between understanding that the diagnosis of stupidity was wrong and actually going back to the beginning with the disposition of a genuine student and trying to build the understanding that the system did not provide. This second thing is more difficult. It requires unlearning a series of habits. It requires tolerating for a time the feeling of not knowing, which a grading system has trained most people to consider unacceptable. It requires asking questions that the social context might make embarrassing. But there is something on the other side of that which Feynman tried throughout his life to convey, not through arguments about the benefits of learning, but through the very example of how he engaged with anything he encountered. He looked at the world as someone who knows he doesn't fully understand it, and who finds that not distressing but fascinating. And perhaps that is what physics, conceived in the way Feynman conceived it, has most valuable to offer. Not the equations, not the configurations, but the demonstration that not knowing can be a starting point, not a verdict.